Um, Hello everyone. So this is lecture 11 of MA 221, and today we'll see some of the applications of what we have learned so far. Okay, so one question that you can ask is, what is the energy expected to move an object? So let me draw it like a sample picture. So say you have some object and you are trying to move that from A to B, say. So say you are applying the force F along this direction. Then the question is, what is work? What is the amount of work you are doing in this case? So the formula for work in simple terms is force times the distance moved, right? So W is F times T, abbreviation for the formula. And the next question would be, what is the units of all of these quantities? Work, force, distance, maybe. Okay, so there are like two standard units. One is like US units, which is for force, we have lbs. And for distance, we have uh, foot. Okay, so therefore, for work, our units will be foot times lbs, as easy as I get. Um, okay, and the other standard way is using metric, okay, which is metric way, where your force has unit newtons. 1 Newton is same as 1 kg times meter per second square. And then your work, and then left, then your work is just Newton times meter, or you can say joules. Okay, abbreviation for that is J, and 1 J is same as 1 Newton times meter. Okay, so basically kind of same thing, different names. Okay, so a little bit justification for that is, when your force is like 1 Newton, then your work will be just force times distance. So it will be Newton times, for distance, the unit should be meter. So Newton times meter, as easy as like it. Okay. Now, if I move forward, then the next thing that I want to tell you is the formula for force is mass times acceleration, also abbreviated as m times a. And so sometimes you'll see the unit for mass is like kg, and for acceleration you'll see just meter per second square. And sometimes this acceleration is due to gravity. So for gravity, the acceleration standard is like 9.8 meter per second square. Okay, cool. Now let us look some example. So here the question is how much work you need to raise a 5 lb calculus book to 6 feet, and the same kind of question, but here you have 2 kgs of calculus book and you have to raise it to 2 meters. Okay, so if I see the first problem, then my force F is 5 lb and the distance I have to cover is 6 feet, right? So if you look back into the first slide, then yeah, your force is in lbs and distance is in feet. So you can straight away use the formula for work. Okay, so simply your work will be F times D, which is 5 times 6, which is 30 feet times lb. Okay, cool. For the problem B, your mass is given as 2 kgs, and so your force F, which is same as mass times acceleration, this should be 2 times g, right? Because here the main acceleration is due to the gravitational force. So therefore, we have standard z, which is like 9.8 meter per second square. So you have like 19.6. And as I said, when you have mass as when you have mass as kg and acceleration, the unit for acceleration is meter per second square, then you can straight away write that as Newton. Okay, cool. So far, so good. Next example, you are asked to find what's the mass of a 5 meter rod um, when you are given that its density is 1 plus 2x kg per meter. So let's try to decode what's in there. So say this is the rod and say the length of the rod. So say I place the rod along x-axis like this and say this is from 0 to 5, right? And say this small um, little portion is dx, and say this distance is x from the origin. Okay. Now, if I ask what's the mass of the small size dx, that is, let's denote that by dm. So dm is basically ex dx, right? Because this small little piece here is having length dx, right? And your density is kg per meter. So like 1 unit of meter have this amount of kgs in it. That's the density means. So therefore, my dm will be ex times the small length. Then basically for total mass, you just have to integrate it. So integration 0 to 5 dm, in other words, 0 to 5 ex dx, which is basically 0 to 5 1 plus 2x dx, which is x plus x square from 0 to 5 is 5 plus 5 square, which is 30 kg. Okay. Why kg? Because the unit for density was kg per meter. So yeah. Now the next set of problems discusses about when you have variable force. Say this is again a little piece on the x-axis, and I mark A and B like that. And say you are applying variable force. That means along the distance, the force is not constant. It's also varying. Then say this little distance is like delta x. Now, in this case, the work done moving from, say, this point to this point, say this point is x, that point will be x plus delta x, right? Yeah, a little bit here, there. Say, this point is x, and this point is x plus delta x. Okay. So that thing is same as fx times delta x, right? Because work is simply the force applied times the distance it covered. So if you take limit delta x tending to 0, then you'll find w to be integration a to b fx dx. Sweet. So this is work done by force fx moving from x equal to a to x equal to b. Okay, cool. The next thing is Hooke's law. This is mainly for springs. So say I have a spring like this. Okay, so this is like origin 0, and this is in equilibrium state. Okay, now what you can do, you can perform basically two operations to this. One is you can just stretch it a little bit. So this is 0. Say this distance is like x. Or you can compress it. So this is 0. And this is again x. So then it's very natural to ask, what is the force applied? What's the work done when you are basically stretching or compressing the spring? Okay, so a spring stretch or compressed a distance x from its rest position needs a force fx, which is same as k times x, where k is spring constant, a quantity that is constant for each of the different spring. So you have, say you have two springs, one on the right hand and the on the left hand. So those two springs may have like different spring constant. Say one for the right one, you have 5 as spring constant, and for the left one, you have say 3. But why they are called constant? Because for one particular spring, it remains constant. Okay, k remains fixed for one particular spring. Okay, cool. So let's see one example. So if you have a spring stretched at 10 centimeter, which exert a force of 40 newtons, then you have this 3 question. A is asking what is the spring constant K? B is what is the work done stretching the spring 20 centimeter? And C is what is the work done compressing it one further centimeter when it is compressed 4 centimeter. Okay, let's handle this one by one. So for A, I know that F is K times X, right? So for A, I have to find the spring constant. Find K. Okay, cool. So a spring is 10 stretched 10 centimeter. So say my X is 0.1 meter because I have 10 centimeters. So I have reduced that centimeter into meter, or rather converted that centimeter to meter, because I have to be consistent with the units. I can't work with centimeter and say later on meter and like have my answer. So yeah, and the force applied was 40 Newton. So remember, in Newton, I have meter cube or something, meter square. So therefore, I need to have that, you know, same units. Therefore, I need to convert this 10 centimeter into 0.1 meter. Anyway, so now from this identity, I have 40 to be same as 0.1 times K. So therefore, K is just 400 Newton per meter. Okay. How do I get this Newton per meter unit from here? What is the unit for force? Let's go back. For force, the unit is kg times meter per second square. Okay. So kg times meter per second square. And then on the right hand side, I have meter. So therefore, I'll just have kg. Oh, sorry, rather. My bad. Okay. What is the unit for force? It's Newton, right? And what is the uh okay. See, I should follow from here only. The unit for force is Newton. I don't know what is the unit for K, but I know that X represents here distance, so therefore meter. So therefore unit of K should be Newton per meter. Right? Cool. That's how we get the unit for the spring constant K. Fine. So part A is sort of done. And we also know that for the force needed will be 400 times X, right? From this line. Okay. For B, question number B, what is the work done stretching the spring 20 centimeters? So work done by stretching 20 centimeter, which is same as 0.2 meter. For the same reason, I need to convert it, is W same as Fx dx, right? One of the standard formulas that we have discussed when your force is varying. Okay, which is what is force? That's that. So 400 times x dx. Now, what is my x? So x is from 0 to 0.2, right? That's the stretch. So you can just calculate this as 20 into 1 x square from 0 to 0.2, and then it will be like 8 joule. Okay. Remember when I'm like working with Newton as the unit of force and distance is meter, then for that case, my unit for work is joule. Okay, fine. Now part C. if you have to compress the spring from 4 centimeter to say 5 centimeter. So spring was like this. The stretch was 4 centimeter from, okay. And now just stretch it further like this. Okay, cool. Let me there. Okay, so for that, maybe I need more space. Okay, for that work is same as, so I have first 0 point, okay, work is same formula 400 x dx, right? But now in this case, what do we have? So if you convert 4 centimeter, it will be 0 0.04 meter and it will be 0 0.05 meter. So I'm going from 0 0.04 to 0 0.05 of that, which will be like 200 x square from 0 0.04 to 0 0.05, which is just 200 times 0 0.05 square minus 0 0.04 square. If you calculate, that will be 0 0.180. Okay, that's the answer. My next section would be, let me just add one page here. It'll be better. The next section is, what about the work required to lift a mass against gravity? Okay. For example, if you have a rectangular shape, um, something like this, having 3 meter, 2 meter, and 6 meter as its dimension. And it has density 500 kg over meter cube. So how much work is needed to build it? Okay, that's the question. Okay, fine. See, for this type of problem, you have to again consider this slight little slice. So this is sort of my slice. Like this. Okay, cool. Ah, okay. And sorry, this height is x meters, say. Then the volume of the slice will be 2 times 3 times dx meter to the third, right? What's the mass? For work, what do I need? Most of the time to evaluate the work, I need force and mass. So the mass of the slice is 6 times dx times 500 kg. Why? Because I know that density is this. which is kg over meter to the third. So if I multiply that with the volume, then I'll get the mass. Okay. Now as the force of gravity on slice, that is same as mg, right? So m times g. What is m? M is this. So I have 3000 times for gravitational force, the acceleration is 9.8 meter over second square. Cool. Which is just 29400 dx. Yeah, there should be a dx there as well. So dx Newton. So far, so good. Then the total work would be just integrating from 0 to 6, because the the slice were like, if you consider the slice was varying over the height 6, right? So 0 to 6, 29400 x dx. Why this x is coming into picture? Okay, rather I just write it down, actually. It'd be better. Okay, so the work done raising slice is what? 29400, and then x dx joule, right? Because the height of this little piece is x. And remember, when you build this block, you go from bottom to up. So therefore, it's just x dx. So for work, generally what we do, force times the distance. So this is like the component of distance. Okay. And then if you integrate, you just get 529,200 joule. Okay. We have a lot of work to do. For the next example, which is pretty interesting, I believe, what you have to do is, yeah, what's the question? The question is, what is the work against gravity needed to empty a 8 by 4 by 5 meter tank full of water through the tap of the tank with a 1 meter high pipe? Okay, maybe let's draw the picture. So the picture is something like this. Something like this. I'm having the dimension 5 centimeter, 8 centimeter, and say 4 centimeter. And there is a pipe like this, which is like draining out all the water inside. Okay, cool. So again, for this problem also, we have to go by taking a small piece. So say this is again my structure of the box. Say this is the small slice that we'll consider. Okay. Okay. And the width of this slice is like X, and it is at height X from the ground, from the very bottom. This whole thing is like 6 centimeter. So therefore this part will be 6 minus X, right? Okay. Okay, so far so good. Now the volume of the slice will be 4 times 8 times dx meter cube, right? By the same logic. And the mass of the slice will be what? So this is 4 times 8 is 32. dx is already there. And the density of the water is 1000, right? So I have to multiply with 1000. So 32,000 dx kg. This is the mass of the slice. Okay. Remember, this slice is like containing basically water, a slice of water you are considering. And now the distance moved. Now the interesting thing is that when you like clean down the water, or like when you try to like empty the tank, then your water level goes from top to bottom, right? So therefore now the distance moved should be this distance, which is basically 6 minus X. Therefore, work done on slice will be 30. Okay, I missed the force though. Okay, I need to calculate the force as well, right? Because what is for work, force is also needed. So the force will be what? Mass times the gravitational acceleration. So 32,000 dx times g, which is 32,000 times 9.8 dx, which is 313600 times e times so let's just write dx Newton, and then work will be just 313600 dx times 6 minus x joule. Okay, so the total work that is needed will be just 0 to 5313600, and then 6 minus x dx. And this is a simple calculation. I hope you can do that. I'll leave it like that then. Probably this is the last example. Yeah. So the last example is, what if you have, instead of box, you have the box in this example. What if you have the same problem, but with the conical structure like this? And say the radius is like 2 meter and the length is 6 meter. Then to calculate, to make things simpler, we'll just take the 2D projection of this, which will be like a triangle having total of 6 centimeter height. And there, if you take a small piece of say dx width, and say this is y, and this length is x from the very beginning, and this is 2. So by similar triangle property, y over x will be just q over 6, because this triangle and the big triangle, which is like, say, this and that. This triangle and the big triangle is similar. So therefore, we'll get this. We'll get this identity. And this implies y is 1 over 3x. Okay, cool. And the volume of the disk is pi y square dx, right? Remember, this is the 2D projection. But if we think about the 3D conical structure, then this is basically a circle having some thickness. Okay. So for that, you'll have a volume, right? So volume of the disk would be pi y square. So the pi y square is basically the area of the circle, and that circle has a width, so therefore volume we have to multiply with 3x. Okay, cool. And in terms of x, this will be just x square over 9 times pi dx using this identity. And then the weight of the disk will be 1000 pi x square over 9 dx kg, right? Because the density of the water is 1000 kg over meter cube given. Okay. Now the force due to gravity, because that is working against water to be pumped out. So that will be just m times a, so 1000 pi x square over 9 dx times 9.8, right? Newton. If you, yeah, I don't want to simplify this further. You can do that, I guess. So just for work done on, say, disk is 1000 pi times, say, 9.8 over 9 x square, and then dx joule. Why this dx? Because f times the distance moved, right? Okay, same thing, same logic. There's a mistake going on. Here also you need to apply the same logic, right? The water is coming from top to bottom, this direction, right? We know that this distance is x, so therefore the other half, that means this distance will be just 6 minus x, right? So just instead of dx, you have to multiply with 6 minus x dx, right? Yeah. Yeah, dx was just carrying forward from here to here. Okay, anyway. So therefore the total work would be 0 to 6, because that's the height of the tank. 1000 pi times 9.8 over 9 x square 6 minus x dx. Okay. And you can just calculate this. This should not be difficult because it's a simple integration. Yeah, so that is it for today, and we have seen some concept of like applying the integrations and stuff to physical world. If you have any questions or concern, you can just meet me in office hours. Okay, cool. Thank you.